The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today we move to a topic I really like. It's the beginning of the applications. So we're aiming for, so the particular application that comes first will be springs and masses, a pretty classical problem. But what we're looking for is how do we model it? What's the main framework to look at a whole series of problems? So this is number one in the series, and it's the most straightforward. Let me draw it with 4 springs connecting 3 masses, and let me fix both ends. So this will be a fixed picture. And the question is, so the masses have some weight. The weight pulls the springs down. When there was no weight acting, they were not stretched. The masses will stretch the springs, and the question is, how much do those? We're looking for the displacements. How much does mass 1 go down, mass 2, mass 3, and of course, essentially the displacement here is 0, and here is 0. So we're looking for this. I don't know if you can imagine these masses have acted. So the position before gravity was turned on was somewhere up here, and then it came here. So this moved down by a distance u1. Let's use u for the displacements. So if I look at this main picture here, I have displacements, movements, u1, u2, u3. Okay. Now, what happens physically? Important in every one of these examples to see what's happening physically. Of course, this one moved down by some u2. This one moved down from its total rest position to u3. These are not oscillating. Next week, they'll start moving. Time will enter. Here, I'm just looking for a steady state. They come to rest. They stretch. So what's your feeling of what's going to happen here? Somehow, the displacements look to me like they'll all be positive. By that, a display. So what's the key equation going to be? That when this moves down, it will stretch that spring. Hooke's law will say there's a force, the spring pulls back. The spring pulls back with a force proportional to the stretch. So U1, U2, and U3 are movements. Now, here's a key question. What's the stretching in spring number 2? So this is spring 1, 2, 3, and 4. How much does spring number 2 stretch? U2 minus U1. A difference is coming in there. So let me put that up here. So stretching, or elongation, I'll use 2 words. Elongation, I'll say sometimes, because that starts with the letter E. So these are the elongations in the springs, in the 4 springs. Okay? So those will be, let me call them, so it's the amount the spring stretches. Or, what's the opposite of stretching? Compression somehow. It looks to me like this last spring, at least, is going to be compressed, and I'm not sure about the others. So we've got 4 springs, and each one has a stretching or compression, elongation, and then there's a link then that you already told me that E2 is just from the picture, E2 is the difference between U2 and U1. Because the lower mass goes down by a distance U2, the upper mass by U1, and the spring is stretched by the difference U2 minus U1. Okay, so that's a first key fact. So that expresses somehow a fact of geometry, of sort of the way things are connected. The material properties of the springs have not got into the picture yet. But now Hooke's law brings them into the picture. By stretching a spring, that produces a force that pulls back. So we get, can I say, forces in the springs. And let me give those a name W. W1, 2, 3, and 4. Okay, and then the link between the stretching and the force that it produces is, okay, so that's somehow where the properties of the material come in. And so I have to say, what are the properties of the springs? So that's, this will be Hooke's law, this step, Hooke's law for this particular application. And so I have to say these springs have spring constants. So I haven't completed the description of the problem until I've told you about the springs themselves and the masses. Okay, so the spring constants will be C1, C2, C3, and C4. And now what does Hooke's law say? Let's just, usually this physical law in the middle, we keep it linear. Of course, we all understand that if these springs were enormously stretched, the elastic property could become nonlinear, it could become plastic. We're always, the first law, it always has somebody's name, was the person to see that in some range of small displacements, so I guess that's the answer. We're speaking here about small displacements, small stretchings, up to the point where Hooke's law continues to hold. Okay, and now what does Hooke's law say? It says that each force in the spring is proportional to the stretching of the spring. So that's, you could say it's a diagonal matrix is showing up here. The vector of W's, the vector of forces in the spring, is a diagonal matrix C, which just has these numbers on the diagonal, C4, times the E's. So of course I'm going to write that in matrix notation as W equals a matrix C times E. So there in the middle is the physics, the material properties, the constitutive law. C can stand for constants, for constitutive law, later for conductances. It's the place where the material enters. And now, how do we complete this picture? In the end, we have to bring in the masses, which are giving, gravity is the external force that's making things happen. I mean, so that's, we need a force term from outside to move us away from zeros. And that will be the forces, the downward forces, F1, F2, F3 on the three masses. Okay, now let's see. Now, so I plan to complete this picture with a force balance equation. Force balance on the masses. on the, on each mass. Okay. When I use the word framework there, this is what I was talking about. I guess what I want to say is, I really have found that this way of describing, of modeling the problem is successful for so many applications. You have somehow a geometry where a step which will involve a matrix A. Then you have a physical step which involves a matrix C. And then finally you have a force balance. In a way, this force balance, or it's analog for, the analog would be Kirchhoff's current law. We'll see that for networks. Flow in equals flow out. Force on one side equals force on the other. If we're talking about equilibrium, we can expect our model to have an equation like that. And for me, it really helps to know when a new model comes in. Like somebody will come into my office with a problem in chemistry or biology, and it'll be this. But if it fits in this framework, I'll be looking for a balance equation, a continuity equation at the end. Okay, so now we have to. This part was easy, and it's these two parts that I want to pin down. Okay, well, you told me how to start here. So the elongation, so I want to take this step. Again, I want to find the elongations from some matrix that multiplies the displacements. So I'm just completing this step. And you told me what is the stretching in spring 2. Again, do you mind just saying it again? The stretching in that second spring, the amount it's made longer by the action of gravity was U2 minus U1. U2 minus U1. So E2 will be a -1 here for U1, a +1, and a 0. That will be a typical row of this matrix that can, the displacement stretching matrix, you could say. Now, what about the stretching in E1? What's the stretching in E1? Only U1, because essentially it's U1 minus U0, but U0 is set to 0 by the support. So we only have U1, because so that multiplication just gives us, so E1 is U1, E2 is U2 minus U1, E3 is what? The stretching in the third spring is what is it? U3 minus U2. So I need a 1 for U3 and a -1 for U2. And the stretching in the fourth spring. What's the stretching in the fourth spring? So again, stretching, I'm thinking, I've sort of, and you have too, mentally given a plus sign when the spring is extended, and a minus sign when it's compressed. Plus for tension, minus for compression. So so since I fixed that one, U4 was 0, so what do I have in this last row? Just minus U3. I guess what I'm saying here is that if we get a systematic approach to problems, then we know we're looking for a matrix that connects these. We're looking for the material constitutive law that does this, and now we're looking for this one. We kind of know where we are, what to look for. And so this matrix is the matrix I'm going to call A. So this is E, equals AU. Okay. Good. Good. Okay. Well, one more step to go. And that will be the force balance step. Okay. So now what's the equation for balance? So the external forces are the masses. Well, I guess to get the units right, it should be mass times g, the gravitational constant. The forces, so let me put force, external forces, F1, F2, and F3. The three masses will be M1g, M2g, and M3g. So those are the forces from outside. Now it's the balance equation I'm after. So this is in this position. It's in equilibrium. And what does that tell us? That tells us that the total force on this mass, so I'm going to take each mass, it's like a free body force diagram here. I'm looking now at that mass. I'm saying what forces are acting on it, and I'm making them balance. So what equation will that give me? So let me write that. This is now the force balance equation. Force balance at each mass. Okay, how much force is pulling up? What's the force pulling up on? So this spring is pulling upwards, and it's pulling upwards by W1, right? Just we're getting these letters right. The W's were the forces, the internal resisting force, reacting force in the spring. W1 is pulling up. What other forces are acting? W2 is pulling down, and also pulling down is gravity, M1g. So the balance of forces there says that W1, the force up, is W2, the force down, and M1g. And similarly, the next one will have the next mass. If I look just at that, I see a force up, a force down, and gravity down. So W2 will be, that's the pull up, will be W3 plus M2g. And the third one, the force up on the third one, will be the force down on the third one. Okay. So I think those are the equations of force balance written one at a time. And now, of course, I'm going to write that so that's three equations with four W's. So I want to write that as, I want to bring the W's all to the left-hand side. Can I do that? So can I just bring those over with minus signs and make these equal signs? Okay, so now we've got internal force balancing external force. This vector of external forces is the F's, and this is the internal forces. Now, somewhere there, we're going to see a matrix. So I'm going to write this equation as some matrix. Well, let's figure out what that matrix is. So its shape is what? I've got three equations, so I need 3 rows in the matrix. I've got 4 W's, so I need 4 columns. So it's going to multiply W1, W2, W3, W4 to give these 3 masses. Can I call them F1, F2, F3, just to have a good letter? All right. We're there, almost there. What's the matrix? What's the matrix for this final step, the force balance equation? Okay, I just read it off. W1 minus W2. I think I've got that. W2 minus W3. What goes in the tell me what the second row of the matrix looks like to give me W2 minus W3. 0, 1 for the W2 minus 1. Good. And for the third, the final row, 0, 0, 1 minus 1. So that completes the third piece. If I had given you the problem, well, as I did, drawn the problem, described it, you know that there's going to be a connection between the external forces and the displacements. But what I'm trying to say is a good way to see the connection is to see it in 3 simple steps. The simple step that gets you from the displacements to the springs. A second step within the springs. A third step back to the nodes, you could say, back to the masses. And of course, the key question is, what's that matrix? And do you recognize that? Do we need a new name for that matrix? The matrix in the third step. So this third step is going to be that some matrix times W is F. And what's that matrix? What's the good name for us to give it? A transpose is the best possible name. If we've given this name, this matrix, the name A, the stretching displacement matrix, the strain, you could, in elasticity, this becomes the strains, these become the stresses. But the beauty is, just beautiful, that the matrix in this law is the transpose of this one. So it's A transpose. So that's the framework seen now here for the first time. So the key point was that A and A transpose both appeared, but with a physical material properties constitutive matrix in between. So if we put the pieces together, then we're golden. Okay. And then let's do an example to see what actually happened. So the equations were E equal AW, E equal AU, then W equals CE, that's Hooke's law, and then or maybe I'll write it as F equal A transpose W. Okay, that's the 3 steps. So in this problem, the source term showed up at that point. The source term came from external forces. Okay, I've got 3 equations. Now I'm going to put them together into one. I'll put them into one equation. So this W, I'll just substitute. So it's A transpose, W is CE, and E is AU. So I have A transpose C AU. So that's the ultimate. That's put the whole structure together. That's the equation you have to solve. This would be called the stiffness matrix. And I use the letter K for that one. Okay. So our equation is KU equal F. This is our final equation, right? Okay. So well, we didn't know W. So so usually there are 2 unknowns here. Two physical things that you want to find. If you're designing a bridge or a structure, you want to know the displacements, and then you want to know the internal forces W. It's really it's really beautiful. The 2 unknowns of U and W are somehow dual. We can work with one, work with the other, work with both. Let me just mention that the finite element method will fit this framework, and somehow this name stiffness matrix has become famous for finite elements in structures, and then it's just exploded to appear all over the place. Okay, so I guess we should look at A transpose CA. We can see what it looks like, and also just from the way it looks there. So I can write it out explicitly. I think we want to. But at the same time, I can learn something from just seeing how it's put together. What can you tell me about A transpose CA? Let's get the shape first, just to see the shape of these things. The matrix A is what? What's the shape of A? It's over here, 4 by 3. 4 by 3. And the shape of C was 3 by 3, is it? From where have I got that C matrix? Better be here somewhere. Oh, no, it's 4 by 4. 4 springs. Of course, it had to be 4 by 4 to do that multiplication. There's the C matrix, 4 by 4, thanks. And the A transpose matrix, 3 by 4, thanks. So the net result is 3 by 3. Good. So it's a square matrix. K. K is a square matrix. What else can you tell me about it? Now now we're going to begin to use some of the sort of the matrix preparation. We now, these matrices are kind of friends by now. This is a difference matrix somehow, right? The stretchings are differences in displacements. That's its transpose. And then the C matrix, which is the new thing, sort of the new guy to appear today, is diagonal. Okay. Well, if I asked you now, without writing out the matrix, for one more property, it's square, what else could you tell me about it? Symmetric is going to be a very good guess, and let's see why. Why is it symmetric? How do we show that? So now what do I do? I take the transpose. So if I take my K transpose, now I write it as, what do? It's a product of things. So when I transpose a product, I have the individual transposes in the opposite order. So A, its transpose comes first. C, its transpose comes next. A transpose, its transpose comes last. So that's just the rules of matrix transposes. Now what? Now I'm ready to use the wonderful fact of what we've got here. So what is C transpose? So notice, we wanted a symmetric matrix in the middle to be able to say to be able to knock that T out. And what is A transpose transpose? That's A. So we've learned that the thing is symmetric, that if I transpose it, I get it back again. Right. Okay. We're going to see more about that. But let me do the multiplication. So I'm going to take that and, oh boy, how am I going to do that? I want to multiply 3 matrices to see what K actually looks like here. Okay. One question first. Eventually, the solution, the short formula for the solution will be U equal K inverse F, right? So the answer will be U equal K inverse F in matrix notation, but I'm looking for numbers. And then if I know U, then I know the stretching. E is A times K inverse F. And W is, I'm just going down the list, is C times A times K inverse F. We've got everything. So that's the key. This is the key equation. That's the answer. Let me ask you about inverses. What about K inverse? We took 3 steps. Now, what if I just ask you about inverses? So this is K inverse that we would like to know. So again, for inverses, I'm gonna start this and I'm gonna stop halfway, and you'll tell me why. I would, if you give me a product of matrices and I don't think particularly much, I'll take the inverse of that times the inverse of that times the inverse of that. And what's the matter with that? That's, you would say, why not just undo each step? Why not find the W's from the F's and then the E's from the W's by dividing, and then the U's from the E's? Why don't we just go backwards around the loop rather than what I'm saying we have to do? We eventually get this step across with the matrix K that does all three at once. Why? Well, sometimes we might be able to, but I don't think we can in this time. What's the trouble with A that I don't want to write A inverse? It's, well, I don't say singular. What do I say here? Look at this matrix A here. It's not square. It's not square. That's right. So I'm not comfortable. I'm not willing to write A inverse for when A is not a square matrix. Okay. So, and this distinction, is the matrix A square or not, is the first issue. It's just a picture. Let me show you an example where it would be square. May I, before I do this multiplication, can I jump to I'll change the line of springs in a way that'll change A. And let me show you what happens. Suppose I take out that spring. Okay. So I've removed the fourth spring. It's a line of springs now hanging from a support. It's a perfectly good problem. It's problem 2, but it's a different problem. And what's different now? There is no fourth spring. If this was my problem, what would be different? There's no fourth spring. So that's gone. I just have 3 springs stretching from 3 masses. Then the force balance is the same. Everything looks the same, except there's no force. There's no fourth spring, so there's no force there. That's gone. And of course, how does C change? How does so in my new picture, now I have let me write now A transpose CA. A is now 3 by 3, right? I've lost a row. A transpose is now 3 by 3. I've lost a column. That fourth spring is gone. And what is C? Well, of course, there's no guy here anymore. What I'm trying to say is, for this problem, the matrices have become square. This would be correct. This is a specially nice kind of problem. It's called statically determinate. It means I can determine the 3 W's from the 3 F's. I can go backwards. Everything is determined. The long word for the fixed one, our main example, is statically indeterminate. I cannot determine 4 W's from 3 forces. I can't determine what these internal forces are until I put the whole loop into one matrix K. Okay, so that's like a warning and at the same time an important separation. A few nice problems where you don't have too many springs, you don't have too many bars in a truss, you just have like the minimum number to hold it together, could be statically determinate and square matrices. But here, we're not square. OK. So now I go back, put that. So that would be fixed free. Right? That example that I just described would be fixed free. And we can kind of carry that along because we know that what happens is we lose a row and a column. And a C4 is just not in the picture anymore. OK, but now I want to go back to put to the fixed one and finish it. So that's got a support down there too. OK. All right. Key question, what's this matrix K, this A transpose CA? We know it's a square matrix, we know it's a symmetric matrix, but it would be really nice to know what does it look like? What does that matrix look like? OK, can I do the multiplication? So this is going to be K. So it starts with a 3 by 4, 1 minus 1, 1 minus 1, 1 minus 1. Then it's got the 4 by 4, C1, C2, C3, C4. And then it's got the transpose of that, which is the 1 minus 1, 1 minus 1, 1 minus 1. OK, with zeros where I didn't write anything. OK, we got three matrices to multiply together. What's going to happen here? Well, let's see. I guess why don't I multiply that by that? Can I do that? So that's like getting two steps together. It's going to be easy because of this. This is usually an easy matrix, often diagonal. So when I do that multiplication, so I'll just copy this guy. And now C1 multiplies that row. C2 multiplies this row. C3 multiplies this row. And C4 multiplies the last row. OK, so that's C1 in that row, C2, C3, and C4. And now I'm ready to put those together into K. So K will be 3 by 3. What does it have? It has C1 plus C2. And then next to that is going to be this row 1 against column 2. There'll be a 0. There'll be a minus C2 here. And then when row 1 goes against column 3, there's nothing. Why nothing? When do I expect to see a 0 in the overall matrix? What is it about? So that 0 is in the position 1, 3. What is it about masses 1 and 3 that is putting that 0 in there, that we kind of expect to see that 0 even before we find it? If I look at the picture, what do you notice about masses 1 and 3 that is going to produce the 0? They're not connected. They're not connected. If I had another spring, which I could have, connecting mass 1 to mass 3, that would produce, I'd have another, I'd be up to 5 instead of 4. That would be a 5th spring. It would have its own constant. It would show up. It absolutely could. Here we don't have it. OK, now let me keep going. I know from symmetry that the second row times this is going to be 0 is going to be minus C2, symmetric as I expected. What are you expecting on the diagonal there? C2 plus C3. That's certainly the right pattern. 0, C2 plus C3. Yeah, C2 plus C3. And what are you expecting over here? Negative C3 is a good guess. It's seeing that pattern. Let's just see it happen. That second row times this third guy will give me 0. I have 2 rows, 2 zeros, and then the minus C3. Good. And now we know the 0 is going to show up here. The minus C3 is going to show up here, and what will show up here? C3 plus C4. Okay. So we've got it. That's the matrix K that controls this whole problem. Now we check it's square, yes. It's symmetric, yes. And notice also it's the kind of matrix we've seen already. In fact, it's exactly the matrix we've seen already if, suppose all the C's are 1. Suppose every C1, C2, C3, C4 is 1. Then what's the matrix capital C in that standard case? C will just be the identity if these are all 1s. And then I'm only left with A transpose A. So let me take that special case below it, just so special if, so this is if C is I, what matrix do we have then? Just to see that we have a matrix that we know about. So I'm copying this now here in the case when all the C's are 1. So if you put all those C's to be 1, what matrix do you get? You get, yes, you get the special K. Right, you get the special. So the work we did to understand that special matrix pays off here, because we know how that matrix works. And this matrix, well, it's got 4 spring constants in it. But we can guess the important facts about this one from this one. So what are the important questions about that matrix? This is my matrix K now. What would be, we know it's square, we know it's symmetric. What else do we ask about a matrix? Is it, well, positive definite, that's the perfect question. Right, and built into positive definiteness would be a property that we mentioned the very first day. Is it invertible? What's your guess? Is that matrix invertible? Everybody's going to guess yes, because, well, if you guessed no, I mean, where would you be? The whole course would end, because I mean, in fact, the world would end, because the problem is correctly posed. Those displacements are determined by the forces, and that just says K is an invertible matrix. So, but how do we see that it's invertible and even more positive definite? Because that's the property we now know. So why is that matrix positive definite? Do we want to check determinants? We could say, okay, that guy's positive. We could evaluate this product and find that it came out well. Would you want to do that one? We could probably do the 2 by 2 determinant. Could you take that times that and subtract that? Let's just write it above what we would get, just to see it. We'd have that number times that number would be a C1, C2, and a C1, C3, and a C2, C2 twice, and a C2, C3, and then I would subtract off this guy, so it would knock out that, right? And it would leave something that would be positive. Yeah, all the spring constants are positive here. We're talking normal materials. I guess actually people are producing now really amazing materials with amazing properties, and the amazing property is a material with a negative C. But that's like, 18085 does not allow such a thing, right? C has to be, all these C's are positive. Okay, and you might guess that the whole determinant is positive, but now I'd like you to tell me why. So now we can use our growing familiarity with matrices to say why is this matrix positive definite? Is symmetric, of course, positive definite. Okay. Why? So that's what the previous lecture helped us to answer. We've got these various tests, but what was the core idea of positive definiteness? The core idea was positive energy. The core idea was I looked at the energy X transpose, no, U, sorry, I have to call it U now. U transpose times that matrix times U. And there was a reason why that matrix was, why this number, it's going to be a number, right? This combination will involve all four of these C's. It'll involve three U's. I don't want to write out that quantity. It will be, you know, I'll have some U1 squareds and some U1, U2. I won't have any U1, U3 because that 1, 3 entry is 0. But why was this positive? Where do I put the parentheses? Yeah. Where do I put the parentheses to see that that's positive? I put them around where? Around that, good. And around this. This is really, since we now have a letter for AU, this is really E transpose C E, right? That's E. This is E, AU, and this is its transpose. And now what? So now we've narrowed it down to C. Oh, we can actually see why it's an energy. Tell me what E, remember C is that diagonal matrix. What will this be? This is the row of stretchings, the diagonal matrix of C's, and the column of stretchings. And now if I do that multiplication, what do I get? Do you see it? This is, because the physics is coming in now. Yeah, what do I get? Yeah, this will multiply that. Yeah, so what's the first term I should write here? E1. What will it be? This is, I only have diagonal. In other words, I only have perfect squares when I look at this thing. I think I just have C1 E1 squared coming from that diagonal, that C1 there, this E1 here, this E1 there is going to give me that C1. What else will I have? C2 E2 squared, C3 E3 squared, and C4 E4 squared. And do you remember about springs and Hooke's law and energy? What's the energy in a spring? It's a stretched spring. So why am I? So the energy in a stretched spring. This is the sum. What I wanted to say. This is the sum of 4 internal energies in the 4 springs, but it properly should have a factor of half. They're probably, to really use the word energy properly, it should be a half of all this. Half of all this. Half of, that's the energy in the first spring, the energy in the second, the energy in the third, and the energy in the fourth. Yeah. But, of course, our matrix point was, it's positive. It's a sum of squares multiplied now by these positive numbers, these elastic constants, C1, 2, and 3, and 4. Okay, So we know the main facts about that matrix. Yeah. Let's see. We could, so we're really at the point here of, we've got the problem formulated. We've got the essential facts about the matrix. It's symmetric, positive definite, certainly invertible, and then there'd be the step of actually computing U by solving the stiffness equation. So this is like, say for example, Professor Bhatta's big finite element code, ADINA. What are the big overall? What's the big picture for ADINA? For any big finite element code, Nastran, ANSYS, whatever. Yeah, Abacus. There are so many really good ones, and they're taken years and years of work to create. But if you look to see what are the elements that go in, you choose the model, and we'll see in the next chapter, in October, we'll see what finite elements is about. You have the material properties. You assemble the matrix, K. That's a key step, is assembling this matrix, K, and then the final step is solve the system, Ku equal F. But it's assembling that matrix. Okay. Now, one thing popped into my head. Do I have time to mention it or not? Maybe we're, and there's no class Monday, I think, right? Yeah. Can I mention, can you hang on one more second to mention a really remarkable way to do matrix multiplication? You may say, we know matrix multiplication. We got it, right? We did it and we got the right answer. Can I just show you another way and you can see if it works? I did this multiplication by, I'll say rows times columns. I took rows times columns. That's the usual way. But finite elements and often the right way is the opposite. It's columns times rows. And of course, this guy is in here too. You might say, okay, what do I get from column 1 times that number times row 1? Can you do that multiplication in your, just mentally? What? Yeah, multiply that column by that row. First of all, what shape will the answer have? What shape will the answer have if I multiply a 3 by 1 times a 1 by 3? 3 by 3, it's a full matrix, columns times rows, and it's a totally legitimate way to multiply matrices. That column times that row will be, well, you can see what will it be, and then the C1 is going to come into it. Do you see what? It'll just be, if I just did those multiplications, it would just be that. And then the C1 makes this, puts that there. What do I see there? I see the element matrix. The matrix, do you see that this is the piece that involves C1 in the answer? Well, I guess you'll see it better when I do column 2 times C2 times row 2. So I have to add that guy on, and then I'll leave the other. Okay, what do I get if I do that column, 3 by 1, times itself as a row, times the C2? I don't know if you see what I'm going to get. If you just do that, you'll see a C2 will appear here, and a minus C2 will appear there, and these will be zeros. So this was column 1 times row 1. This is column 2 times row 2. We've got the third and then the fourth. But do you see that this part is telling me all about the second spring? This part is telling me what does the first spring, the C1, contribute to K. This part tells me what does the C2 part. You see the C2 part in K? there, minus there, and minus there. The third part from the column row would be the C3 part, and the fourth part from the fourth spring would be the C4 part. So that's a way you won't have thought of, but it's the way Adina would assemble this matrix. It would not do that multiplication. It would do it this way, columns times rows. OK, we'll see it again. So hope you have a great weekend and a holiday Monday that we all happy about. OK.